Whenever you see an alcohol and a reaction arrow with H2SO4, what should you guys immediately think?
E1.
E1 elimination, you are going to form a double bond that OH is going to leave. That's all you should think about whenever you see that.
And then that double bond, it formed, oh God, it
Right.
formed, okay, yeah.
Oh. All right. Let's go back to. Okay. Let's take a look at our next one. So now we have alkynes. So alkynes are going to be, all right, alkynes. Alkynes react very similarly to alkenes. All right. If I can think about how alkenes react, alkynes are usually going to react the same way, just twice. All right. Melissa, are you okay? Okay, just making sure. I know that everyone's reaching their breaking point right now. This is normal at that time of semester, and with pandemic, I know it can't be any easier, particularly if you're trying to do it at home or if you're away from home. There's no like happy middle ground, right? In terms of you want to be home, but at the same time you want to be at the privacy of your apartment or dorm. So it's never easy. Okay, so hydrogen and platinum. What do those react? What does that reaction do? Does anyone remember?
I'm sorry, what did you say? I'm like completely just like.
Hydrogen and platinum.
Oh.
Doesn't it get rid of the double bond?
Yeah.
Mm-hmm. But I have a triple bond here, so what's going to happen now?
Is it just going to become a double bond? Or is it
Nope.
going to become a single bond?
Would you form like two products?
It's going to make it to a single bond. 2, 3, 4, 1, 2. Oh, no, added a carbon. This is not fun to draw. 1, 2, 3, 4. So hydrogen and platinum, H2 and platinum. It'll turn any alkene or alkyne. The only thing it will not affect, if you see this, if you see benzene ring like this, this will not react with these. Any other double bond or triple bond will completely go to alkanes. All right, so they will completely disappear. Does that make sense? Okay. Now, this is where you've got to keep tricky. So these three make one really great card in case you want to make one for your reactions, or 3 individual cards. What's the difference now when I add Lindlar's catalyst?
Does it cleave the triple bond?
It will still react with my triple bond, but now it's going to stop at the alkene. And it is now going to give me the cis. Lindlar's catalyst is what's called a poisoned catalyst. Essentially what happens is that it can react with alkynes, but it cannot react with alkenes. So once this alkyne reacts and forms the alkene, the reaction stops. And you always get a cis alkene, cis. So to think about it, the hydrogen and platinum, the one we just did before, you would form this as an intermediate, and then it would form this. But this Lindlar's catalyst, it poison, and it just stops right here. So you always get the cis alkene. So Lindlar's catalyst and H2 will never react with any alkene, only alkynes. All right, and our next one, sodium and ammonia. Can anyone predict what the product is going to be?
I had a quick question on the last one. Is it H3 or H2?
Oh, sorry, that 3 did right all the way.
Okay, sorry, I just wanted to make sure.
No, it's fine. Okay, and now anyone have a guess what's going to happen with sodium and NH3 in ammonia?
I think that doesn't completely get rid of the triple bond and make two products.
Nope.
It's gonna
okay.
be trans.
Yep, you are going to keep your single bond, as that happens for some reason. You are going to keep your, but now, so this now is that it's going to become a double bond, but now it's going to be trans. So it'll give you the trans. So H2 platinum, all alkynes and alkenes that are not part of conjugated rings become single bonds. H2 Lindlar's catalyst, only alkynes become cis alkenes. Sodium and ammonia become trans alkenes.
So basically, when you have a catalyst, you have a double bond, but if you have a poisonous one, you get a cis.
Poisoned.
Yes, if you have that, then you have a cis. But then if you have another kind of catalyst, then you will get a trans.
Yep.
Okay.
So these are the three that they always teach. So these are the ones you need to remember. These are very specific reactions. Don't worry about the mechanisms because I think they're like 12 steps. So no one makes you learn them. Because that's just insane. That's just mean. That's beyond my level of mean. All right. I figured there'd be more people here tonight because it's a week of a test. Maybe I haven't been helping them enough, so they're like, eh. Okay, predict the major product formed in each. Indicate if the reaction undergoes SN2, SN1, or E2. So for some reason, you don't have to worry about E1. So what is our product going to be? We have ETO, sodium, and heat. Let's think about this. So ETO minus an Na, is that a good, well, actually take a step back. First thing, as I said, is let's take a look at our carbon that our leaving group is attached to. What type of carbon is that? Methyl, primary, secondary. Secondary, I think.
Secondary.
Yeah, okay, I saw your pencil and I was like, set 3? Nope, that's not a finger, that's a pencil. It's a secondary, so we didn't eliminate anything, all right? Now we have ETO-Na. So is this gonna be strong nucleophile, strong base, weak nucleophile, weak base, or if you can't distinguish strong or weak? We'll start there. Is it strong or weak?
Strong.
It's gonna be strong. Is it a strong nucleophile or a strong base?
Nucleophile.
I'm gonna be very upset at you guys if you don't get this right for one very important reason.
Is it a base because it has an A?
It's ETO minus. What did I tell you about ETO minus? I gave you guys a very specific slide on this.
Wait, can it be either?
It can be.
It can be both, right? This can be both strong base, strong nucleophile. What are my other two? Don't forget this. NaOH, NaOMe, and NaOET. All right, these are the three that you always have to ask yourself, is it going to be a strong base or a strong nucleophile? Now, this is something I said a little bit earlier, and maybe you didn't catch on to it when I was going through my elimination reactions, but which one's going to be preferred now, SN2 or E2, and what's the key?
E2 because of the heat added.
Yep, E2 prefers heat. So when I add heat, E2 is going to be my reaction. So now we have one more thing to worry about. Zaitsev or Hoffman product, because when I see that this is my alpha carbon, I have two betas. This is a beta, this is a beta. This beta here is a secondary, and this beta here is a tertiary. So will this be the Zaitsev product or the Hoffman product? And why? Well, you don't know.
I'm gonna say Hoffman.
Wouldn't you have both, but one's major and the other one is minor? Oh, I see. It's asking for the major product.
Mm-hmm.
Zaitsev?
So there are two types. Zaitsev and Hoffman, right? Zaitsev will go after the more substituted one. So my base would attack the tertiary. Hoffman would go after the least substituted, the secondary. What tells me which way this reaction goes? Zaitsev for Hoffman. What reagent tells me? My base. my base is going to tell me whether or not it's going to form the Zaitsev product or the Hofmann product is the major product. So ethoxy, sodium ethoxy, right? This is the OET minus. Is this a small base or a bulky base?
Bulky.
Nope. What was the one thing I told you that you need to look out for to see if it's a bulky base?
Oh,
Oh, T-butyl.
If I see
T-butyl.
isyl or tert butyl in the name, that is my dead giveaway that those are going to be bulky. So sodium ethoxy, not bulky. It is going to form the Zaitsev product. All right. So OH, OME, and OET for your own records now, they are small, strong bases. They prefer E2. They will always form the Zaitsev product as your major product. So coming in here now, my product is simply going to be, and I'm going to draw a very simplified version because I'm way too lazy to draw the 3D shape of this after you form the double bond, because you technically form something called the bow tie, but I don't think you guys have even learned that anyway. You are going to form this essentially as your product. And actually, this is how you should draw your product because it's going to be inaccurate if you draw it the other way. Okay, questions on that one? Is your anger at the chemistry starting to gear towards me now? I've seen it happen before. You wouldn't be the first group of students I've helped where the anger is just spread. Okay. Did it at least make sense though to walk through and say what's happening each step of the way to say is it SN1, SN2? Okay, that's the way we should do all this. So let's do the next one. We'll see if maybe your luck improves. Okay, what type of carbon do I have here with my leaving group?
Secondary.
Secondary, all right? So I didn't eliminate anything. Now, potassium, and what's OTBU?
that's a tert butyl.
It's a tert butyl, but that's not the full name.
Oh,
Tert butoxide.
Tert butoxide, yep, tert butoxide. So tert butoxide, so what type of reagent is that? Small base, or weak base, strong base, weak nucleophile, strong nucleophile?
base? Oh, wait.
I'm gonna say a strong base as well.
It is just a strong base. It is only a strong base. Because remember, tert butoxide, remember the other three that we talked about in the last problem, those are the only ones that we ever say, those are the ones that we have to worry about being strong nucleophiles, strong bases. Right? So now, if this is a strong base, we have a secondary carbon, what type of reaction is going to happen?
SN2.
Strong base, secondary carbon, E2. Remember, strong base, secondary carbon, it's going to be E2. All right, so now we know that this is going to be an E2, but now we have a problem. We have a tertiary carbon for a beta carbon here and a primary for this beta carbon. So which way is our double bond going to go? Towards the tertiary or towards the primary?
Towards tertiary.
Is this bulky or small?
Oh, it's bulky. So
It's bulky. We're going to go towards the small direction.
Yeah.
So we are going to form the Hofmann product as our major product, like that. Questions on that one? Concerns on that one? Okay. Let us go to our next one. All right, for our next one, again, secondary carbon, and this is something that I warned you guys about, right? Is that it would be nice if you got methyls and primaries and tertiaries thrown in there. But as I said before, it's just one of those things where secondaries are great for teachers because they work for all of them, so you can't eliminate, but that's okay. CH3SNA, what type of reagent is this? Weak, strong nucleophile, weak, strong base. No idea.
Could it be both a strong base and strong nucleophile because of the sulfur?
Okay, so is this one of the three that I told you about earlier?
No.
So again, Matthew, this is something that I really, really want you to commit to your memory. These are the only three common reagents that you will ever have to worry about that question. These are the only things that are both strong bases and strong nucleophiles. And I suggest making a card and committing that to memory, just because that is, that's where they can trick you on that one, right? But this one, no. This one does not fall into the category. This does have something. Does this S have a charge or not?
Yeah.
Yep, because remember, whenever you see a metal, the metal is a plus charge, right? And then whatever is next to it is going to be a minus charge. Anytime you see an S minus, you should automatically think strong nucleophile, S, strong nucleophile. So what type of reaction is this going to be now?
SN2.
SN2, strong nucleophile, right? Secondary carbon. And also we have polar aprotic solvent. So our reaction, other stereocenter is going to stay the same. We are going to invert. So now this is going to be SCH3. So in one of those sheets I sent you, I think there's a list of all of the common strong nucleophiles and all of the common strong bases. So it might be useful. I know that this test throws a lot of information at you. But just do the best you can. Okay. I'm gonna let you guys sit on this one for a minute on this next one. Think about type of reaction it's gonna be. Walk through the same checklist we did. Remember, think about what type of carbon it's attached to. Think about the reagent. See if there's anything else after that. So go through the carbon substitution, then think about the reagent. And if you get stuck there, then look if there's anything else that can help you make a prediction. Okay. Guys need a little more time, or are you good? Another 30 seconds, or you as far as you're gonna get? I'll give you another 15, 30 seconds, just if you're still kind of. All right. So what type of carbon is my iodine attached to?
Primary.
Is a primary. So what should you immediately think? What just got eliminated?
SN2.
SN1. SN1 got eliminated, right? So we are in SN2's house or E2's house now. Okay. Simple enough. NaOCH2CH3. Strong base, strong nucleophile, because that's the only thing it can be, right? Because we can only do SN2 or E2. So is this a strong base or strong nucleophile?
Both, right?
It is both. That is correct. Remember, this is one of our ones that can fall into either category. So here's the tricky part. What is favored now? SN2 or E2? Think back to all that I have taught you. Think back to the first problem we did.
E2.
What was in that first problem that we just did here that's different from this one?
There was heat.
There was heat. So since we don't have heat, what's favored?
SN2.
SN2 is going to be favored. Also, remember I said when it's a primary carbon, it's going to favor SN2 unless you add heat to it. So now we are simply going to just replace it with our OCH2CH3. Does that make sense? Okay, so again, this is just a step-by-step process. Don't make it more complicated, and don't try to do all the steps at once. Do it one step at a time. All right. Don't go beyond your, like, don't think I have to immediately figure out what it is when I make a decision on what type of carbon it is, or what type of nucleophile or base or whatever it is. Just do it step by step. Okay. I'll let you guys do the next one. I'll give you guys a minute for the next one. So go and work on that. It's only Tuesday, guys. We have tomorrow and Thursday. UCLA is winning against Michigan right now at halftime, only by 4 though. So I don't know if any of you guys really watch college basketball though. So that may mean nothing to you.
I've only been interested in the drama surrounding the women's basketball thing for college.
Ah,
It's weird how like they only got like a dumbbell rack and like guys got like a whole like weight room. That was so
I mean, that's like normal. So I did college. I did marching band and pep band when I was in school, because because I've told you many times. But when we went to the NCAA tournament, when we went to the women's tournament, we got a per diem of $35 a day, meaning we got free hotel, obviously, and they drove us everywhere we needed to for games and stuff. But we got a $35 per diem for food. Like, we just got an envelope that said, TV or ill, $35. So every day we were at the tournament, we got paid $35, and that was our for food, whatever money. When we went to the men's tournament, it was $60 per diem. A part of it is there's more viewership in the men's game right now. Obviously, there's going to be more money involved because those contracts are more spent. But at the same time, you're right, is that the basic resources that the university gives its people should be the same. Right? Like, you think about the weight rooms and all that stuff, and it didn't really take much to do that, and they got it settled. So that's what Title IX was all about, but we still have those issues, unfortunately. But if you watch women's basketball, more often than not, there's a little less drama in the games, because usually the better seeds usually win. You have a lot less upsets in the women's game. I miss watching women's Pac-10 Pac-12 basketball. It was a long time ago, last time I went to one. So what type of carbon is my leaving group attached to? So you guys don't care about basketball right now. It's secondary, so we did not eliminate anything. All right. So now, strong base, weak base, strong nucleophile, weak nucleophile.
Strong nucleophile.
Nope.
It's not both?
Because you have a metal here, you have a hydrogen here. Remember, when you just have the hydrogen, it's weak.
Yeah.
Like all of you. Just kidding. That's cruel. So when we think about it, when you have the protonated oxygen versus the negative charge one. This is the strong one. This is the weak one, right? So when you have the protonated one, that's always the weak one. So ethanol, weak base, weak nucleophile, all right? So this is going to be a weak nucleophile because it said only worry about SN1, SN2, E2, right? It said don't worry about E2. Sorry, E1. So this is going to be a weak nucleophile. So what's going to happen in my first step? This is going to pop off, right? And an SN1. So now I'm going to get ooh, that's bad. This. So what's next? What's the next thing that's going to be happens? Going to have a methyl shift because it's a secondary next to a quaternary. Like that. And now this is going to attack. So then my final product is going to be this. Like that. Oh. There we go. So this should be my final product. So think what carbon you have, primary, secondary, tertiary, methyl. That will help you eliminate some stuff, hopefully. Then think about, do I have a strong or weak nucleophile, strong or weak base? Once you do that and you say, all right, figure out what's happening. If it's an SN1 or E1, you always have to think rearrangement's possible. See if that's possible. If it's SN2, flip your stereo centers if you have them. E2, draw your base, draw your double bond to the more substituted carbon with small bases, to the less substituted carbon with bulky bases. I know that that's a lot of information, but those are the key things to remember, right? So this should be your final product here because you did have a methyl shift. Because we had a rearrangement. Okay. Can I erase this or are you guys still? All right. Mags, how you doing?
I'm doing okay.
All right. Reaction. I forgot what these are called. Reaction trees. So basically, we all start with the same product, and we just have to think what each of these are going to do. So let us go through and talk about them one by one. So BH3, THF, H2O2, NaOH. What are we adding to our double bond?
An OH group?
We are adding an OH group. So I'm going to draw my product because we're not doing anything to the actual like single bonds. Those are all going to stay in place. But now, are we adding the alcohol to the tertiary carbon or the secondary carbon?
The secondary carbon?
You are correct. BH3, hydroboration. Whenever we see BH3 and THF, we know that we're adding an alcohol. This is the anti-Markovnikov one. Do you remember that? This is one of the few reactions where we add our big group to the less substituted carbon. Fun fact, hydroboration was discovered, well, not discovered, but was really, a lot of research was done by a man by the name of Dr. H.C. Brown. He is the grandfather of Purdue chemistry. So I got to hold his Nobel Prize and sit in his office chair when I went to Purdue. You're not supposed to do that. They got very angry at me, but I did it anyway. I didn't know that you weren't supposed to. But it was kind of cool because I've held a Nobel Prize. It's really nice. I'll never win one. I'm not smart enough to win one, but they're really cool. I did get to have a class taught by the other Nobel laureate we had at our school, which was Negishi. H. Negishi. Very nice old Japanese man. He's unfortunately at a very old age now, so he's not doing so well, but very nice man. You'll learn about Negishi's reaction maybe this semester or next, but okay, HCl. This is the hydrohalogenation. So what are we going to do in this one?
I have a question on the one we just did.
Mhm.
So there's like a little like cheat sheet towards the end of our notes where it kind of summarizes like every single reaction. And I just looked at it right now and it's like the same reactants and like solvents. And it said that it produces an enantiomer.
Oh, yep. So here's what's going to happen is that when we add this, we can add the OH on a wedge. On the other side, we are also going to add an H, and they're both going to be on wedges like that. So what's the other way we could add them then?
Just the other
Dashes.
Yeah, dashes.
Does that make sense?
Yes.
Yeah. So because you're going to make a weird intermediate, so you can add it either that way or that way. But your H and your OH that you add across that double bond, because we are adding them to here and here, they're both going to be on wedges or both be on dashes. So what you can do is you can say this plus an N. Shorthand. You don't have to draw the other way. And you really don't need to draw this unless she tells you to. So you can draw this and say plus an enantiomer or something like that. Did you know that? All right, HCl, what are we going to do there?
Is it just gonna attack?
We're going to add the HCl across the double bond like we did in the last one. But the Cl, does it go to the more substituted or the less substituted?
Substituted.
It's going to go to the more. Like that. So now the only thing is here, you don't need to do what? There's no enantiomer in this one because you make a carbocation. So when you make a carbocation, essentially every form of this molecule being made is there's no stereospecificity.
I have a question.
Yes.
When you have a peroxide, does it go to the less substituted side?
That's correct. So if you have HCl and then you have some type of peroxide down here, like this, or H2O2 or something like that, then you would just flip the chlorine to the other side. Does that make sense?
Yeah.
Okay. Okay, so I'm going to clear this off of here. Okay, going down, we get this product, but what should go over the arrow?
H2 and platinum.
Yep, we go from alkene to alkane, so H2 and platinum. Tasty, tasty platinum. Okay, next one is a halohydration. We're adding a chlorine and an alcohol. So our product, again, we're going to keep our same. Which carbon gets the chlorine? Which carbon gets the alcohol?
The alcohol goes on the more substituted side.
You are correct. Melissa, you need to sound a little more confident in yourself. You're getting these out right.
I'm just getting them right because I literally have the little like note sheet next to my screen looking at them.
That's all right.
That's how I'm gonna try to pass the exam. Because technically that's not cheating, those are my notes.
I'm not your supervisor. I will have to say you have to do what the professor tells you because I'm not your professor, but
I think it should be okay. We have this up because it is in the PowerPoint slides and it is open now. So
oh, well then there you go.
Dr. V,
Mhm.
for this next one that we're doing, I had a question
Mhm.
about it because I was working on like practice exams on the test, and one of them was instead of being OSO4, it was KMNO4 and then dash NaOH, and then under the arrow it was cold.
So that's a
does that-
completely different reaction.
So does that mean that you don't have an enantiomer at the end, but you have two OHs?
Yeah, so when we do this one, right, we're going to do the OH here. We're going to add two alcohols, right?
Yeah.
When we do this one. So let's just do this one first. So they are both going to be on wedges or dashes. So you're going to get either or. One will have both on wedges, one will have both on dashes, right? And the other one was, you said it was KMNO4
Yeah, and then NaOH
and cold.
and cold, yeah.
Okay. So in this case, when you do this one, I think in this one, they're both going to be this. It's going to be the same thing.
Okay.
They'll both be wedges. They'll both be dashes. Sorry, I just had to think about that for a second.
So what does like cold mean? Like,
Temperature.
well, yeah, but like, what's the
ice
difference
bath?
between heat and like cold? Like,
Just think about what's cold to you and what's hot to you. So room temperature is kind of like our middle ground. So if it's
Yeah.
colder than room temperature, it's cold. So like 0 degrees, or if it's warmer, like 50